Hi everyone, it's my great honor to stand here and present our group's recent work, local algorithm for structure preserving graph cut. So here's the outline of my talk. I will start with a brief introduction about the background and the related works. Then I will introduce the proposed horseplot algorithm. At last, I will show some experimental results and finally conclude this paper. So networks everywhere. Graph present a powerful data structure for model the relationships among entities in the real network, such as internet, social network, and online transaction network, and so on. So dense subgraph detection is very popular in practice since it provides an important tool for us to understanding the underlying structure of the given network. For example, on the web graph, the emergent trend detection aims to find the hot topics that are growing in interest or utility over time. In social network, community detection aims to find a group of users that are tightly connected together. In online transaction network, money laundering detection aims to find the group of malicious bank accounts that are frequently involved in the money laundering activities. Sometimes, higher-order network structures is more important than we only do some machine learning stuff by extracting features based on the nodes level or the edges level. For example, on the web graph, it appears that when a set of increasing set of star-shaped structures showing in a short burst may indicate the hot topics or trends. Thus, by exploring the dense subgraph that contains the rich star-shaped structures helps us to locate the trends and hot topics. Another application is the community detection. So it has been proven that the triangle plays a fundamental role in the social communities. So if we can find dense subgraph that contains rich triangles, also helps us to locate the social communities. The last application is the money laundering detection on online transaction network. So we observed that from our experiments that the directed loops showing this kind of network may be red flag for the money laundering activities. So if we can explore the loop-shaped structures and we largely include this kind of structure in the returned cluster, then maybe we can locate the malicious money laundering bank accounts. So here is our study problems generally. Suppose we are given the graph G, user-defined structure N could be anything like triangle, loop, star-shaped structures, anything, clique maybe. And our target is to find a structure-rich dense subgraph that largely preserve the user-defined structure. So let's take an example. The left-hand side is a given graph, and the right-hand side, the user-defined structure as like a 3-node line. And what our target is to find the dense subgraph that contains rich 3-node line, just as in the red circle. So now I'd like to show some related works. So higher-order graph clusterings. This problem has been studied for a while. They are very important because it's improving our understanding about the high-order organizations of real networks, such as frequency-based method, spectral clustering-based method, and the co-clustering-based method. Well, the bad news is that when we're considering like higher order structures, the time complexity is always expensive. Another local graph clustering is another important family of approach for the dense subgraph detection problems. Since they are attractive, since the running time does not depend on the size of given graph. And but to the best of my knowledge, before this paper, there is not like a local graph clustering framework has been proposed in the literature that are modeling and addressing the problems regarding the high-order network structures. So can we do like combinations? Like can we extend the local graph clustering mechanisms to model and explore the high-order network structures? Would that be cool? So in our paper, in this paper, we present a local algorithm named the horseplot. And we can find the structure-rich dense subgraph and only runs in polylogarithmic time with respect to the number of edges. And here is our I'm going to show some details about our Hausblock algorithm. So Hausblock stands for high order structure preserving graph cut, local cut. And before we go into more details, I'd like to first introduce the evaluation matrix which we design and use for our problems. So the case order conductance. For any cluster C on a graph G and the user-defined structure N, the corresponding case order conductance is defined in this equation. What? Okay, anyway. And in the numerator, it indicates the number of network structure N destroyed due to the partition of the graph G into G and G bar, where G bar is like the complementary set. And the denominator contains two terms. The first term indicates the number of network structure N in C, and the other term is the number of network structure N in C bar, and we choose the minimum value. So let's take an example. Still the previous graph, and here is the cut. Make the graph into two parts, C and C bar, okay? And here is the definition. So when we consider the network structure N is edges, then it's just like totally the same as a traditional conductance definition. The result is 1 over 4. So when we extend to high order, when such as like the third order network structure, 3 node line, then then it changes. So in the denominator equals 2 because there is 2 3 node line is broken due to the partition, which is 2, 0, 1, and also 0, 1, 3. So 2 broken. And in the numerator, it equals 3 because for the smaller set, the blue nodes only contains 3 node line. So the final result is 2 or 3. By using this kind of matrix, it helps us to largely preserve the network structures we want in the certain applications and to make them rich in the return cluster. So we call it like our problem is like structure-rich graph cut problem. And we redefine our problems by using the metric of case order conductance. So suppose we have the graph G, user-defined structure N, and also initial vertex V. We're using the local graph clustering mechanisms. So our target is to locally explore the network around the initial vertex until we find the dense subgraph that satisfies our criterion. So to explore and modeling the high-order networks organizations in the given network, we use the techniques of high-order random walks. So here's definitions about the adjacent tensor and transition tensor about high-order random walks. So here is the adjacent tensor definition. So basically, each entry of adjacent tensor indicates whether the set of nodes I1, I2 until IK can form a user-defined structure N or not. If yes, equals to 1. If not, equals to 0. Using the previous example. So for the set of node 2, 4, 1, the entry equals 0, since the node 2, node 4, node 1 cannot form a 3 node line in the given graph. And for the set of nodes 6, 8, 10, the entry equals 1, since they do form a 3 node line in the given graph. And here is the definitions about the transition tensor. So basically, the transition tensor is like column-wise the stochastic version of the adjacent tensor. So so still using the previous graph, I'm sorry, there is some problems about the presentation due to the size of the. So using the previous examples, so the transition tensor, the entry of a transition tensor is equals of node 2, node 4, node 1 equals 0 because the numerator is 0 and denominator is not 0 by the definition. And for the set of nodes 6, 8, 10, the entry equals 1 or 3 because the numerator equals 1 and the denominator equals 3 because by using node 6 and node 8, there is 3 ways to form a 3 node line on the given network. And the high-order random walk could be also be interpreted as a case-order Markov chain. So we consider each vertices as like an individual state, and each entry of the transition tensor could be interpreted as like a conditional probability. So using the previous example, for the entry P142, it could be considered as the conditional probability of a given node 4 and node 2. What's the probability to form a 3-node line using node 1? So the answer is 0. And for the entry P10A6, it could be also understood as like a given node 6 and node 8. What's the probability to form a 3-node line by using node 10? So the answer is 1/3. Because you can see we have 3 ways to form this kind of structure by using given node 6 and node 8. And to reduce the space complexity, we adopt the rank 1 approximation, and we formulate the high order random walks as the first equation. And to further enhance the efficiency, we also introduce like a truncation operator for conduct the high order random walks to reduce the time complexity. And the epsilon is like a truncation threshold, and we want to round all the small values to 0 to reduce the computational load. Our framework is designed based on the vector-based graph cut mechanisms. So first, in each iteration of our algorithm, we will firstly conduct a one-step high-order random walks to explore the neighborhood of the initial vertices. And then we will compute the permutation pi of the returned high-order random walk distribution vector Q by this way, where D is indicate the degree of each vertices. And after that, we will generate a series set of cuts, C1, C2 until Cn-1. And we will check the potential cuts until we find the cut that is satisfy our criterion. And here is the proposed algorithm. But I don't want to go through it. I make a simple demo for better illustrating it. So suppose the user-defined structure is 3-node line, and the bottom one is a given figure. So we will first do the initialization, which calculates the initial truncated local distribution vectors. And then we will conduct high-order random walks to explore the neighborhood of the initial vertex 0. And after that, we will do the vector-based graph cut. If we can find the cut that is the cluster that is satisfy our criterion, minimizing the higher case order conductance, then we will return it. If not, we will go to the next iteration and do the high order random walks and the vector-based graph cut again. So in our papers, we also show some theoretical bounds regarding our algorithms. In theorem 4, we show that suppose we have a cluster C on the graph G, and we choosing an initial vertex V that comes from the diffusion core from the cluster C. And when some mild condition is satisfied, we show that the volume between the C and between the intersection of C and C prime is larger than 2 to the B minus 1, where the C prime is the cluster returned by the non-empty cluster returned by our algorithms. And the B is like a constant which controls the minimum volume of the returned cluster, and it is decided by the user. And then in lemma 5, we also show the time complexity of our algorithms, which is here. So it appears that our algorithms could run in polylogarithmically with respect to the number of edges on the given graph. Now that I show some experimental results. So here is the dataset we included in our paper. So we using like citation networks, infrastructure networks, social network, review network, and financial networks. Here is a comparison method. We're using 3 local graph clustering methods and 2 global graph clustering methods. And TSC and the Hotspot, our methods are both high-order graph clustering mechanisms, and we're using the same high-order network structure, 3-node line. Our triangle as user-defined structure, I'm sorry. So here is the effectiveness analysis. So in the top 2 figures shows the result of conductance of edges and the conductance of triangles. The result is the lower the better. And in the bottom figure shows the triangle density. The result is the higher the better. I will show more details. So for these 3 figures because it's so small. And we can see that our method is like outperform all the others in all the cases and all the metrics. And here is the first figure. Let's show some examples. So for the first network, airline, we can see our algorithms is 97% smaller than another high-order graph clustering method, TSC. And in the second metric, our algorithm is 12.2% smaller than the second best. And in the last metric, for the last figure, our algorithm is 80% larger than the second best. So we can see our algorithms outperform all the others. And we also find two another interesting observations. First is that for both local, our local algorithms performs better for both the high order and the lower order graph clustering method. Local algorithms performs better than the global algorithms in respect to the three metrics, the conductance and the triangle density. And another observation is that the high order graph clustering method do performs better than the regular graph clustering method especially when we consider the triangle density and the high order conductance. And here is some scalability analysis. So here we're using Nibble as our comparison method because Nibble could be considered as like a special case of our algorithm. The reason is two. One is it is also like a local graph clustering method. Another is because it only conducts lower order random walks. So here in the scalability analysis, we consider it as like a faster version of our algorithms. And in the first figure, we show the running time versus the increasing size of given graph. We can see the curve is like increasing polylogarithmically. So it's also consistent with our time complexity analysis. And in the second figure is a log-log figure. The horizontal axis indicates the log of the volume of the return cluster, and the vertical axis indicates the log of the running time. We can see the red curve is like around like linear. So it demonstrates our time complexity is polynomial with respect to the volume of the return cluster. And here is parameter analysis. So we studied the parameters of the input conductance. So in our algorithms, we have an input of the input conductance upper bound. So this parameter controls the upper bound of the conductance of the return cluster. So we have two observations. The first one is our algorithms converges faster even with a very loose upper bound than Nibble. And another observation is that our algorithm always performs better. I think a simple guess is because our algorithm is more able to explore the high order structures, which make the cluster to be more compact and dense. And because previously we all talking about the triangle as the network structures, and here we will show some two interesting case studies that's using higher order network structures. The first one is the community detection or movie review networks. So basically, movie review is like a bipartite graph. One side is like the movies, and another side is users. And we're using the structure of a four-node loop. So we can see when both user 1 and user 2 likes the same two movies, then that forms a loop in the movie review networks. So we want to find the clusters that the group of users have the similar taste on the movies. And here is like a miniature of the identified cluster by using our algorithms. We can see there is a lot of these kind of structures in the return cluster. And we also find in the find clusters, most of the users like the movies regarding about the actions and adventures, something like that. And another interesting case study is about sincerity detection. This is a co-work with the Bank of America. So they have the data about they want to find these synthetic IDs. Synthetic IDs generated by some malicious users that stealing the information from real identities and to make some faked IDs and steal monies from all the others. And we're using the structure of the 5-node star. And here is the return cluster by using our algorithms. We can see in the cluster, there is a lot of users share the same name, same address, and the same phone number and the same email, which is very suspicious to be considered to as like synthetic IDs. So now I'd conclude this paper. So our selling point is first, we conduct high-order random walks, and our algorithm is also scalable to large networks. And in our paper, we also show some theoretical bounds regarding the effectiveness and efficiency. And at last, we show a lot of experiments and also case studies, parameter analysis of our proposed algorithm. Thank you.